All right, today we're going to go on a quest to find the hidden truth, to pull a clear signal out of a world that's full of noisy, imperfect clues. And our guide for this entire journey? A really powerful set of tools called Kalman Filters. So let's get started.
Ever wonder how your phone's GPS nails your location, even when you're downtown, surrounded by skyscrapers that are bouncing signals all over the place? I mean, it shouldn't work that well, right? But it does. That's the exact problem we're diving into, finding the real answer in a super messy world. Now, this whole quest has a technical name. It's called state estimation. The state is just the hidden truth we're hunting for, like your exact position or how fast you're going. And the estimation part, well, that's our best guess at that truth using all those messy measurements. This is a huge deal in pretty much everything from robotics to finance.
Okay, so time to meet our first detective on the case, the classic Kalman filter. It's been around since the 1960s, and it is the original, and I mean the most elegant solution for a very specific kind of mystery.
The thing is, the Kalman filter is a master detective, but it shines in a well-behaved world. It's the absolute perfect tool when the thing you're tracking moves in a predictable, straight-line kind of way. We call that a linear system. And it also needs the noise, the uncertainty, to follow that nice classic bell curve pattern, which is known as Gaussian noise.
At its core, the filter's doing this really simple but beautiful two-step dance, over and over. First, it predicts. Based on where it thinks you are now, it guesses where you'll be in the next instant. Then, it gets a new measurement from a sensor, and it updates. It corrects its own guess. Predict, update, predict, update. It's this non-stop loop of refining its own answer that makes it so incredibly powerful. So how does it know how much to tweak its prediction? That's where the secret ingredient comes in. Something called the Kalman gain. You could think of the Kalman gain as the filter's brain. It's this one number that brilliantly decides how much to believe the new measurement versus how much to stick with its own prediction. It's all just a very, very smart balancing act. And this is where the genius of that balancing act really comes into play. If your sensor is giving you garbage data, that's what we call high measurement noise, or R, the Kalman gain gets low. The filter basically says, whoa, I don't trust this new reading, I'm going to stick with my own prediction. But if the filter isn't very confident in its own prediction, that's high process noise, or Q, the Kalman gain goes way up. The filter says, you know what, my guess might be off, I'd better pay a lot more attention to this new measurement. It's constantly adjusting its own level of trust.
The classic Kalman filter is, honestly, amazing. But what happens when the path isn't a neat, tidy, straight line? When the real world gets messy, chaotic, and non-linear? Well, that's when our quest gets a whole lot more complicated.
So let's bring in our next tool, the Extended Kalman Filter, or EKF. The EKF has this really clever trick up its sleeve. It basically pretends the messy, curved path is a straight line, just for a tiny fraction of a second. At every single step, it just draws a straight line to approximate that curve. It's kind of like trying to walk a winding road by only taking a series of tiny straight steps. But this whole pretending thing has its price. The more curvy or nonlinear the system actually is, the worse the EKF gets. The act of pretending a curve is a straight line can itself introduce some pretty big errors. And on top of that, it requires some seriously heavy math called Jacobians at every single step. It's not easy.
And that problem leads us to this, a really profound shift in thinking, which is captured perfectly in this quote. Basically, instead of trying to simplify the system by making it a straight line, what if we just tried to get a better picture of the uncertainty itself? This is a huge philosophical leap that takes us to our next filter.
And that idea brings us to the Unscented Kalman filter, or UKF. It does exactly what that quote suggests. Instead of dumbing down the system, it works harder to understand the uncertainty. It strategically picks a handful of sample points, called sigma points, that perfectly capture the cloud of our uncertainty. Then it pushes those points through the real messy system, no approximations, to get a much, much better final picture. The advantages here are massive. The UKF is often way more accurate than the EKF, especially when things get really curvy. And maybe the best part, you don't have to calculate those nightmare Jacobian matrices. It just works. It's a more powerful and often smarter way to handle the exact same problem.
Okay, but what if the world isn't just nonlinear? What if the noise itself is completely bonkers unpredictable? For the most chaotic, wild scenarios out there, we need our most powerful tool yet. We're going to need the power of particles.
Yeah, just imagine the uncertainty isn't that nice, clean bell curve anymore. What if it has two peaks, or it's totally lopsided?
This is what we call non-Gaussian noise, and it completely breaks the rules that the other filters rely on. We need to throw the rulebook out the window.
This is where we bring in the particle filter. Instead of trying to use a neat math equation to describe the uncertainty, the particle filter just goes for brute force. It unleashes this massive swarm of possibilities, literally thousands of individual guesses, which we call particles, to represent all the places the true state could be.
So here's how this swarm thinks. First, you just create a giant cloud of particles, representing all the possible answers. Then, you move every single particle forward based on your prediction. Next, you look at your real measurement from the real world and you give a higher score, or a weight, to the particles that ended up being close to it. And finally, this is the secret sauce. You resample. You create a brand new swarm by killing off all the bad guesses and making copies of the good ones. It's literally survival of the fittest for your best guess.
So we've met the whole family of filters now, from the old school classic to the brute force swarm. So how in the world do you know which detective to put on the case? Well, it's all about picking the right tool for the right job.
Think of this table as your ultimate cheat sheet. If your system is linear with nice, predictable noise, easy. Use the classic Kalman filter. It's the best, and it's simple. Is it getting a little curvy? The EKF is probably fine. Is it super nonlinear? The UKF is almost always going to be a better bet. And if your system is just pure chaos with bizarre noise, well, the particle filter is your sledgehammer. But just know, it's going to take a lot of computational power. It's always a trade-off. You're balancing accuracy against complexity.
And one last thing, how do you know if your filter is even doing a good job? Well, you can compare it to this theoretical speed limit for estimation, called the Kramer-Rao lower bound. This thing basically tells you the absolute best case scenario, the perfect score that any filter could possibly achieve. If your filter is getting close to that bound, you know you've got a fantastic solution.
Okay, so we've been on this pretty abstract journey hunting for hidden truths. But why does any of this actually matter? Well, it turns out that this quest for estimation is quietly running almost everything in our modern world.
Seriously, every time you pull up GPS, a Kalman filter is working for you. Those autonomous cars you hear about, they are loaded with these things, fusing together data from dozens of sensors. They're used to navigate spacecraft, to help robots build maps of places they've never been, and even in finance to try and predict the stock market. From medicine to military radar, these filters are absolutely everywhere.
So, our quest has shown us that from the simple, elegant, classic filter all the way to that brute force particle swarm, there's a tool for every kind of mess the world can throw at us. And the core idea is always the same: finding that hidden truth by striking the perfect balance between what we think we know and what the world is actually telling us. And that brings us to our final thought. Right now, we use these incredible tools to estimate the state of cars, markets, and airplanes. So the question is, as our world gets even more complex and even more full of data, what are the next hidden states we're going to need to estimate? In biology, in our climate, in our own societies, what's next?